Hello, and welcome to the first Cosmic Adventures lecture for 2024. I'm Dr. Mindy Townsend, the astronomer with Dudley at Siena. So 2024 is going to be a big year because of a solar eclipse that will sweep across North America on April 8th. Everyone in the lower 48 states will experience at least a partial eclipse. And it's the last time that something like this is going to happen for a couple of decades at least. So it's a pretty big deal. To get us ready for this rare event, I'm going to spend the first few lectures of the year talking about eclipse-related topics. I'd like to start the series of lectures by talking in some depth about the celestial body that forms one half of the eclipse equation, and that is, of course, the sun. A total eclipse, of course, is when the moon moves into a position such that it completely covers the sun. Western New York, as you can see kind of on this map, Buffalo, Rochester, Syracuse, and up north are in for actually quite a show. Down here, where I am based in the Capital District, we are set to get about a 96% partial eclipse just before 3:30 in the afternoon on April 8th. This should result in something that's pretty neat, but don't for a second think that it's a substitute for totality. If you've never seen a total solar eclipse, it gives you a view of the sun that is essentially impossible any other time. The sun is quite a typical yellow, what astronomers call G-class star, sitting right here on something called the Hertzsprung-Russell diagram, or the HR diagram. So this type of HR diagram illustrates the correlation between brightness, or equivalently size, with something called a spectral class, or equivalently temperature. So you have spectral class here on the bottom and the corresponding temperature in Kelvin up here at the top. The sun, as I said, is a yellow G-class star sitting right here on something called the main sequence. So this line right here represents the main sequence. Stars that exist along this are really in the prime of their lives. As stars age, they will evolve off of the main sequence, but our star, the sun, is firmly planted right here for the time being. So the sun is a big ball of mostly hydrogen and some helium. It takes 100 Earths to span the sun's diameter, and the sun is 330,000 times the mass of the Earth, weighing in at almost 2 nonillion kilograms. That's a 2 with 30 zeros. It plays host to 8 planets and an untold number of dwarf planets, asteroids, and comets. The sun is in some ways an extremely boring star, and that's a good thing. It makes it possible for life as we know it. The sun is the source of a vast majority of energy that makes life go on this planet. No sun, basically no life. It emits almost 400 septillion watts of energy. So that's 400 septillion joules radiated by the sun per second. And that's a 4 followed by 26 zeros. This is a huge amount of energy. And I mean, the sun is a star, so it's pretty big and it's pretty hot. And maybe this huge amount of energy should not be that surprising. The surface temperature of the sun is about 5,800 Kelvin, or 5,500 degrees Celsius, or 9,900 degrees Fahrenheit. But the mechanism by which the sun stays so hot was unknown for a long time. And there were a few different hypotheses of what's happening in the sun that were kicked about. One mechanism astronomers explored was something called the Kelvin-Helmholtz contraction. A Kelvin-Helmholtz contraction is a process by which a star's gravity creates pressure and heat in the interior. So as a star cools down, the internal pressure holding the star up will decrease, and gravity will start to compress the star, and the star will shrink. The compression will cause the interior to heat up again, which the theory went makes the sun hot. So this seems simple enough. The problem is that if you calculate how long it would take the sun to radiate away all of its energy at its current brightness, we have a star that will only last 25 to 30 million years. By the time astrophysicists had worked this out, there was pretty good evidence that the Earth was several billion years old. The Kelvin-Helmholtz contraction simply doesn't give our solar system enough time to evolve to its current state. But never fear, we have other options. So what about chemical burning? Okay, so a clarification. Astronomers, myself included, will say things like a star burns through its fuel or something like that. But we don't mean burning in the chemical sense. So burning is an exothermic chemical reaction. So it's like a chemical reaction that produces heat, and it requires fuel and oxygen. When you light a match, for example, this is burning. It's a chemical reaction between oxygen in the air and the fuel on the match head. So astrophysicists explored this idea that the sun may be so hot because it is literally on fire. But this is somehow worse than the Kelvin-Helmholtz contraction. The sun simply doesn't have enough stuff to sustain the type of burning that's needed to produce the brightness for very long. It can be sustained for maybe 10,000 years. So for those of you keeping track, that is much less than the 25 to 30 million years that we get with the Kelvin-Helmholtz contraction. And even that wasn't enough to account for the evolution of the solar system. So chemical burning is out. So how else can we get energy? We have one more play, thanks to Albert Einstein and his special theory of relativity. So according to this theory, mass and energy are essentially equivalent. Mass can be converted into energy by the famous equation E equals mc squared, where E is energy, m is mass, and c is the speed of light in empty space. Okay, cool, yes. So what type of process will convert mass into energy like this? Well, the answer is thermonuclear fusion, of course. So what is thermonuclear fusion? So it's fusing together two light atomic nuclei to form a heavier nuclei. And that in that process, energy is released. So in this process, the mass of nucleus 1 plus the mass of nucleus 2 is more than the mass of the heavier nucleus 3. The missing mass is converted to energy according to E equals mc squared. What is happening, though, is that there is a difference in the binding energy, or the energy it takes to tear apart a nucleus, of nucleus 1 and 2 and nucleus 3. So nucleus 3 needs less binding energy, so some energy is simply radiated away. It's not needed. Nuclear fusion can result in the release of actually quite a lot of energy. It's been kind of the holy grail of sustainable, long-term, clean energy production. But it's extremely hard to create the right conditions for it on Earth. It needs a place of extremely high density and pressure, like the center of a star. Under these conditions, atoms are completely ionized, or they're completely stripped of their electrons. You need high temperature and high pressure to force all of these positively charged nuclei together. Remember, positive charges repel, so you need a lot of pressure to push them together. But this works. For the sun, at this stage of its life, hydrogen nuclei fuse together to make helium nuclei in a process that converts a small amount of mass into a large amount of energy. Over the lifetime of a star, there are a couple of different nuclear fusion processes, but the sun is currently going through one particular phase of its life where the dominant form of energy production through nuclear fusion is called the proton-proton chain, or the PP chain, or hydrogen burning. But remember, not real chemical burning, right? The PP chain is called this because it starts out as the fusion of two hydrogen nuclei, which are just individual protons. Remember, hydrogen is the lightest element. Its nucleus is generally just a proton. The chain consists of three reactions that result in the conversion of six protons into a helium nucleus plus two additional protons. Okay, step one in this chain is the fusion of two hydrogen nuclei to make the nucleus of something called deuterium. So deuterium is basically hydrogen with an extra neutron. So how does this happen, right? You start off with two protons, you should end with two protons, right? Not necessarily. The two proton combination is actually not stable, which causes the nucleus to lose energy. That process causes one of the protons to turn into a neutron, which is a more stable configuration. This generally is called beta decay, and this type of beta decay in particular is called proton conversion. So you have this collision of protons that turns into a deuterium nucleus plus something called a positron and a neutrino as a result of the beta decay. That deuterium then needs to collide and fuse with another proton, which results in a helium-3 nucleus and a gamma ray, or a high energy photon. Steps one and two need to happen at least twice, because for the third step to happen, we need two helium-3 nuclei. So step three involves the fusion of two helium-3 nuclei into one helium-4 nuclei and two protons, which can then get right back in the mix and start this process over again. In the end, this process converts four hydrogen nuclei into one helium-4 nuclei, two high-energy photons, and two positrons and neutrinos, which were the product of that beta decay. These two little gamma rays are the energy released by thermonuclear fusion. So how much energy do we actually get from this process? So the mass lost in this reaction is about 4.8 times 10 to the negative 29 kilograms, which is the difference between the mass of four hydrogen nuclei and one helium nucleus. This is 0.7% of the mass of four hydrogen nuclei. If we just plug that into E equals mc squared, we get something like 4.3 times 10 to the negative 12 joules of energy. So this might not sound like a lot, but for something the mass of the sun that is made up almost entirely of hydrogen, it actually adds up. In fact, a kilogram of hydrogen reacting in this way will produce 6.3 times 10 to the 14 joules of energy. And to produce the observed luminosity of the sun, it would have to consume 600 billion kilograms of hydrogen every second. But remember, the sun is 2 nonillion kilograms. At this rate, the sun has enough hydrogen to keep it shining for another 5 billion years. Given that we think the sun is about 4.5 billion years old, we have a solidly middle-aged star on our hands. For thermonuclear fusion to take place, it has to be pretty hot, over 10 million Kelvin. The temperature on the surface of the sun is about 5,800 Kelvin, so this fusion has to happen inside. We can't actually see very far beneath the surface of the sun, though, so we have to kind of use what we can see and the laws of physics to figure out what the inside of the sun looks like. And there is one thing we can definitely see about the sun. The sun is not undergoing any dramatic changes. So what I mean by that is the sun isn't expanding or collapsing, and it's not significantly cooling down or heating up. This means that the sun is in two different types of equilibrium: hydrostatic equilibrium and thermal equilibrium. Both of these are important for our model of the sun. So let's start with hydrostatic equilibrium. This is just a fancy way of saying that the internal pressure of an object exactly balances the force of gravity that wants to collapse the object inwards. So the sun is a star, it has a lot of gravity, but the inside of the sun is very hot and heated gas expands. That hot gas creates an outward pressure that balances gravity so the sun doesn't collapse in on itself. And that's what this cartoon is trying to show. You have this fusion reaction inside. It's producing a lot of heat, a lot of pressure inside, and that pressure inside is exactly balancing the gravitational force that wants to push in. And so we have this nice, stable star. As you get deeper and deeper into the star, the pressure gets higher and higher. And the more pressure means that the gas will heat up more and more. So there's actually a temperature gradient in the sun, but at any given depth, we can assume the temperature is pretty much constant. It doesn't change with time. So this is called thermal equilibrium. So we assume the sun is in thermal equilibrium because we don't observe it getting hotter and colder with time. For this to be, the energy generated in the interior of the star must be transported to the surface in some way, where it can be radiated out into space. The sun will transport its energy in a couple of different ways, which divides the sun's interior into different zones. The first zone is the core, so it's the very center of the star. This is where the energy is produced. It is very, very hot, about 15 million Kelvin. It's about 14 times as dense as lead, with a pressure of about 10 billion atmospheres. And for reference, one atmosphere is the air pressure on Earth at sea level. So 10 billion atmospheres is a lot. This is where thermonuclear fusion takes place in this high temperature, high density environment. Outside the core, it's too cool for fusion to take place, but the energy generated there um, must travel through it to be radiated away, right? Energy must travel to the next zone, the radiative zone. This is the region of the sun where the energy transport process called radiative diffusion dominates. So in and near the core, atoms are stripped of their electrons because it is so hot. So these electrons can't capture photons. The result is the slow migration of photons through the radiative zone. The migration is slow because this region, while not hot and dense enough to fuse nuclei together, it's actually still very dense. So a photon is kind of bouncing around like a pinball. It takes something like 170,000 years for the energy generated in the core to travel through the radiative zone. So light, which we generally think of as very fast, moves only about 50 centimeters per year in this zone. As we go further from the core, the temperature decreases. At some point, it gets cool enough for electrons and protons to come together again and form hydrogen atoms. Hydrogen atoms are really, really good at capturing energy. So they will absorb the light coming from the radiative zone and become more energetic. They become hotter. The hotter material will travel to the surface, while the cooler material will sink in a process called convection. So that's what's happening right here in this outer layer. So now we are in the convective zone. Energy can be transferred to the surface of the sun and radiated away. So understanding these regions of the sun, it's critical to understanding how stars function, but we cannot actually see it, right? We mostly can only see the outer parts of the sun, the solar atmosphere. There are three layers to this atmosphere, right? The photosphere, the chromosphere, and the corona. The photosphere is the lowest of the three layers, and it is the surface of the sun that we can actually see. All visible light that we see is emitted from this layer, but it also emits light from across the electromagnetic spectrum. So this is a relatively cool layer ranging from about 5,800 Kelvin at the bottom to 4,800 Kelvin at the top. Absorption features in the solar spectrum, so these dark lines here in this kind of rainbow strip, they originate in the photosphere because it's cool enough to allow atoms to absorb light at various wavelengths. The photosphere consists of very low density gas, and yet we cannot see through it very easily. We can only see about 400 kilometers into the photosphere. It does not allow a lot of optical light to get through. Next up in the atmosphere is the chromosphere, which is about 1/10,000th as dense as the photosphere. The spectrum of the chromosphere is dominated by emission lines, which is what happens when atoms drop an energy level, so when they lose energy. There's actually one emission line in particular that we see a lot of, which is called the H alpha emission line. And its wavelength is about 656 nanometers. And so that's in the red part of the electromagnetic spectrum. So when we image it, it kind of looks pink. So when you see an image of the chromosphere, it might look pretty like pinkish, like this, like a salmon color. And we can image the chromosphere of the disk of the sun if the disk of the sun is blocked by either a filter on a telescope or, as luck would have it, during a total solar eclipse, like the one coming up in April. So it extends a little bit from the disk of the sun. It looks like this kind of pink hair that you can see around the dark disk. This image also shows the outermost region of the solar atmosphere called the corona. So this region extends several million kilometers from the sun and is about a millionth as bright as the photosphere. This too can only be seen if we somehow block out the disk of the sun, like during a total solar eclipse. So if you can make it into the path of totality, you don't even need any special equipment to see the corona. During totality, when the moon completely covers the disk of the sun, you can just see this wispy streaming gas of the outer solar atmosphere with just your eyes. The corona is fairly hot. It's about 2 million Kelvin. And this means that some of that coronal gas will be flung out into space as solar wind. So solar wind isn't wind like we think of it. It's basically just charged particles hurtling through space. The sun will emit about 1 million tons of this material into space every second. So the sun may be a relatively quiet star, but that doesn't mean that it's not going through its own cycles and processes. The sun is still a very dynamic thing. One of these cycles is the solar sunspot cycle. So roughly every 11 years, the sun's magnetic field flips, meaning that the sun's north and south poles switch. This switch affects the activity on the surface of the sun, like sunspots, which are caused by the sun's magnetic fields. As the cycle goes on, the number of sunspots we see increases. The main visual indication of this cycle is the number of sunspots we see on the surface of the sun. A sunspot is a cooler region on the sun's surface, and they are caused by the twisting and mangling of the sun's magnetic field from within the sun's convective zone. Individual sunspots can last anywhere from a few days to a few months. As you can see from this image kind of at the top here, sunspots are these darker regions on the surface of the sun. They're often the size of large planets. A plot at the bottom here shows the solar cycle since the early 1600s until about 2010. You can see just the dips, the valleys, and the peaks of this roughly 11-year cycle. Sunspots are actually the subject of an unsolved astronomy mystery. So from about 1645 to 1715 was an unusually inactive time for the sun called the Maunder minimum. From about 1672 to 1699, we only saw 50 sunspots on the sun. In modern times, we'd see tens of thousands of sunspots during a similar time frame. So, and astronomers still don't know what caused this minimum. But this prolonged period of inactivity did still show an 11-year cycle. You can kind of barely see it on the graph here. And we've had much more obvious peaks and valleys ever since. It is just still one of these unsolved astronomy mysteries. We don't know what caused it or if it will happen again. The cycle starts with something called solar minimum. During this time, we don't see very many sunspots. In the middle of the cycle is solar maximum, where we see many, many sunspots. So this image on your screen is comparing the solar minimum from December 2019 with the previous solar maximum from April 2014. You can see basically no sunspots during solar minimum, and you can see many gigantic sunspots at solar maximum. The difference is very stark. The intensity of solar maximum isn't necessarily the same every time it comes around. Some solar maxima are incredibly intense, and others are just not. So you can see from this zoomed in solar cycle plot that the 2014 solar maximum was not as intense as years past. You had some very intense ones in the 80s and 90s. The reasons for this aren't clear, and predicting the intensity of sunspot activity is notoriously hard. In fact, the red line here is a prediction of the next solar maximum. It was predicted to be 2025, 2026, and models weren't predicting anything very intense. Looked like it should be something more akin to 2014. However, Scientists now think that we are entering a solar maximum a year or so early, and that it will be actually fairly intense. Over the next year or two, we can expect to see an increase in sunspot activity on the surface of the sun. Now, this can be viewed with a telescope with a solar filter, and maybe even with your eclipse glasses if you have good eyes. Sunspots are also associated with more intense aurora, so more intense northern and southern lights. Auroras are caused by the sun hurling tons of plasma into space and those charged particles interacting with Earth's magnetic field. The sun is constantly flinging plasma into space via solar wind, but the really big plasma flinging event, coronal mass ejections, start as sunspots. Coronal mass ejections occur when the sun's magnetic field gets so twisted that it has to realign. This can cause a star like our sun to eject literally tons of plasma, tons of charged particles out into space. This ejection of plasma is a coronal mass ejection, and they happen a lot where the sun's magnetic field lines get all twisted, like around sunspot groups. So, when we enter the solar maximum phase of the solar cycle, there's an increased chance of very intense auroras. This means that the northern lights could be brighter and could be seen farther south than is usual. Forecasting aurora is difficult, and it can only really be done reliably an hour or so in advance. The Space Weather Prediction Center at the National Oceanic and Atmospheric Administration has a handy dashboard where you can follow aurora predictions. They include a handy chart of something called the Planetary K-index. This index tells us the intensity of geomagnetic storms, these events that hurl plasma towards Earth and are associated with aurora. The lower the planetary K-index, the milder the geomagnetic storms and the milder the aurora. To have the possibility to see auroras in upstate New York, where I'm based, and really the rest of the northern US, we need a K-index of 8 or 9, which is the very tippy top end of the scale. So this is a plot of the K-index for a couple of days back in May, and you can see it doesn't really get too much over 3 in that time. So that was too low to really reach upstate New York. So here are examples of how the K-index affects where aurora show up. So the green on these images shows a low probability of aurora, and the red is a high probability. So the K-index of 3 over here, that kind of produces a pretty weak aurora. To see the northern lights here in upstate New York, we need something closer to an 8 or a 9 K-index. So the storm we need to get this type of atmospheric event is pretty large, but given that we are moving into an era of solar maximum, I think it's worth keeping track of. There are other flashy behaviors that correspond to sunspots as well. So solar flares occur in complex sunspot groups and hurl vast quantities of particles and radiation into space. They can be extremely energetic. The most energetic can be like 100 trillion nuclear bombs going off at once. So a lot of energy in those. Similar but different is a solar prominence, which are these gigantic big loops of plasma. You see the approximate size of the Earth here. So they are truly gigantic, that occur near sunspots that can last for weeks. They're anchored at both ends in the photosphere, and sometimes they can break and fling plasma and particles into space. So the sun is firmly in the middle of its life. We've established this. We have a long time before all of its nuclear fuel is spent and it enters the end of its life. But we think we know what's going to happen when that time comes. So the sun won't explode in a supernova. It doesn't have enough mass for that. To explode in a supernova, you need to be a very massive star. But in about 5 billion years, hydrogen fusion in the core will stop, and the sun will contract under its own massive gravitational force. It will release energy and cause the sun to get brighter over the next billion years or so. When the sun turns into a red giant, it will have swelled to engulf at least Mercury and probably Venus. The sun will spend about a billion years as a red giant. So here on your screen, it's kind of a plot of how bright the sun will get as it ages. And we are right here where this yellow dot is. And right here is where the sun, so-called, leaves the main sequence, that it's when it becomes a red giant and becomes much brighter. So after this phase, the sun has maybe 120 million years left, but it's a very busy time. So first, the core will reignite in something called a helium flash. So right here on this plot, the helium flash. This is a very brief nuclear reaction in which helium fuses into carbon, and the sun will get much brighter, but the sun will, after that's done, shrink, although it will still be about 10 times its current size and 50 times as bright as it is now. The helium flash doesn't eliminate all of the helium, and over the next 100 million years or so, helium will continue to fuse into carbon. When the helium is gone, the sun will repeat that expansion that happened after the hydrogen was exhausted. So at this point, Venus is definitely toast. Over the next 20 million years, the sun will become increasingly unstable. It will lose mass very quickly and will start to pulse. It will kind of enter this stage right here. It will increase its size and brightness each time a little bit more dramatically than the last. These pulses will push away the star's outer envelope of gas, and it starts to make a planetary nebula. So examples of planetary nebulae are right here on your screen. This phase is thought to last only about 500,000 years. The remnant at the center of the nebula is a white dwarf, cooled to about 100,000 Kelvin, encompassing just over half the mass of the sun in an object about the size of the Earth. So it's an incredibly dense, what we call compact object. And there it will sit, glowing because of the residual thermal energy from earlier in its life. But if the universe is around long enough, even that will fade. So not even the sun, one of the few things that we can really kind of count on from day to day, lasts forever. I'm glad this eclipse is kind of giving me an opportunity to talk about the sun, because it's something that I think we can really kind of take for granted, but it's actually pretty cool. If you have a telescope with a solar filter, you can see sunspots and keep track of them yourself. If you have good eyes, and if there's a particularly big spot, you might even be able to see them with your eclipse glasses. If you can see the eclipse during totality, you'll be able to see that wispy, elusive solar corona. The sun has an awful lot of power over us, right? A particularly strong coronal mass ejection will not only make the aurora more intense, but it could also mess with our satellites. Human used to worship this thing as a god, right? And for good reason. It's something that is easy to forget is there until it's gone, which is one of the things that makes a total solar eclipse so arresting. I want to put up this map again of where the path of totality in April is with respect to us. So if you can make the drive, I suggest you do it. So the dark line here, this represents the like kind of the beginning of the path of totality as it goes through the state of New York. And anywhere here, kind of upstate New York, down in New York City, Ithaca, these areas are not in the path of totality. If you can't travel, which I understand is not an option for a lot of people, the entire state will still see about a 90% partial eclipse, which is enough to notice, right? Having a 90% eclipse you'll still notice it getting dark. So I encourage you to get some special eclipse viewing glasses and enjoy the show just from where you are. I sort of think a solar eclipse is simultaneously one of the least accessible big astronomical events and one of the most accessible. Only a few people will get to be in the path of totality. It's a very small strip across the globe. It's about 100 to 115 miles wide, which is not very much in the span of the entire Earth. But when it's happening, you don't even really need anything special to experience it. It's great to have eclipse glasses. Those offer you a great experience, but you can also just poke a hole in a piece of paper and make a pinhole viewer and watch the entire process be projected onto the ground. If you're in the Capital District on April 8th, you'll experience about a 96% partial eclipse, which I want to emphasize is not nothing. I'm not going to be here and tell you that it's as good as totality because I mean it isn't. Totality is really something else, but it will give you a taste of a world with no sun, which is possibly really a once in a lifetime event. So that's about all the time I have today. I want to wish you guys a happy new year and thank you so much for hanging with me. Next month, I want to continue talking about the solar eclipse that's going to happen in April. And I want to talk about the second half of our eclipse equation, which is our marvelous and mysterious moon. I'll see you then.